What do you see up on the board here?
An atom.
Yeah, it's a picture of an atom. Somebody said this morning it looks like the solar system, except in the solar system you don't have two planets orbiting on the same plane. But that's okay. It does look something like the solar system, but it's meant to be the atom. In the middle of the atom is, what's that called? Yeah, it's called the nucleus. And inside the nucleus we have what? We have protons and we get neutrons. Those protons are positively charged. Those neutrons are neutral, right? We have what is it that's orbiting around the outside of the nucleus? Yeah, those are electrons. And the electrons are negatively charged. Good. Now, when we study electricity, we're going to be studying primarily the electrons. Electrons, electricity. It's not a coincidence that electricity is called electricity. And the reason that we're studying electrons primarily is because if something's going to move around and something's going to do what happens in electricity, then it's going to have to be the electrons. Does anybody tell me why? Like looking at this diagram or knowing what you know from chemistry or something somewhere else, can anybody tell me why it's going to be the electrons? If something's going to move around, when I rub a balloon against my hair, okay, if something charge transfers from one thing to the other, the hair to the balloon or the balloon to the hair, why is it going to be the electrons, Bryce?
The electrons are the easiest to remove.
Yes, the electrons are the easiest to remove. They have what we call an electrostatic force. We'll learn more about the electrostatic force later on in this unit, but that electrostatic force, or the electric force, attracts the electron to the nucleus. And the reason for that is because the nucleus is positively charged as a result of those protons, right? That's attracted to the nucleus. That's what keeps them in orbit. You have to have a centripetal force. Remember that from Physics 20? You have to have a centripetal force keeping something in orbit around something else. And that centripetal force in this case is caused by the electric force. But the protons are kept in the nucleus, as are the neutrons, kept in the nucleus by something called a strong nuclear force. We're going to say the strong nuclear force attracts the nucleus together. We're going to learn more about this in our final unit of the year. But for now, you just need to know that that's what keeps the nucleus together. Now, in this context, this isn't always the case, but in this context, the strong nuclear force ends up being bigger than the electrostatic force. So if you pump energy into this by rubbing it against your hair, or if you just have a battery across something that allows the electrons, something charges to start flowing, it's going to be the electrons, because the electrons need less energy to do something, to start moving, than does the protons in the nucleus that are attracted by that strong nuclear force. Now, in the end, it is possible to have protons move. It is possible to have the number of protons in the nucleus change. But if that happens, that isn't an electrical interaction or not even a chemical reaction. Then we've got a nuclear reaction. And nuclear reactions don't happen by rubbing a balloon against your hair or by putting a battery against a couple of wires, right? That's a whole separate thing that we will, again, talk about some in our final unit of the year. But that's not what we're talking about here. Okay, under normal circumstances, that isn't going to happen. Under normal circumstances, it's going to be the electrons that move, because the electrons aren't as tightly bound to the nucleus as the protons are to each other and to the neutron. Does that make sense? So, by and large, this is what we're focusing on this year, or this semester, or this, whatever I'm talking about, this unit. Okay, this unit. Now, where does charge come from? Well, charge comes from protons and neutrons, right? But specifically, where does positive charge come from? Positive charge doesn't mean that you have just protons. You almost always have protons, neutrons, and electrons. You almost always have all three. But you can have positive charge and still have electrons. When I rub a balloon against my hair, either my hair or the balloon becomes positively charged. That doesn't mean that there's no electrons or neutrons. It just means when we have positive charge that we have more protons than electrons. Now, how did that happen? If this thing started out neutral, how do you get more protons than electrons? Protons transferred from one thing to the other to give you more protons? No. What happened? Yeah, the electrons transferred. So if it became positively charged, did it gain or did it lose electrons? It must have lost electrons, right? If you gain electrons, you're going to become negative, right? Gain negatives, you're going to become negative. This happens because we lose electrons. Now, if you have something that's negatively charged, right, rub that balloon against your hair, one becomes positive, one becomes negative, and I don't remember which is which, bless you, but one becomes positive, one becomes negative. One of them has lost electrons to become positive. The other one, either the hair or the balloon, has become negative. In other words, it has more electrons than protons. And that happened by gaining electrons. Do you guys recognize what I mean by that symbol? E with a little negative. Of course, neutral, okay, it's kind of logical at this point right now. Neutral is where we have an equal number of protons and electrons. We haven't gained or lost electrons because we have the same number of protons as we have electrons. Now the unit of charge is called the Coulomb. This is a unit that's like meters per second for speed, right? The unit for speed, meters per second or kilometers per hour. The unit for distance is meters or kilometers, or even something like light years. The unit for energy is joules. The unit for momentum is kilograms meters per second or Newton seconds. The unit for charge, probably never heard of it before unless you've mentioned it in chemistry, is called a Coulomb. Now, that's not in your normal frame of reference. You probably haven't heard that before, so you don't have a concept, an internal notion as to how big a Coulomb is. Whereas we do have a notion internally as to how big, say, a kilometer per hour is. If I say a car is traveling at 70 kilometers per hour on the road, you kind of have a feel for how fast that's going, right? Too fast, too slow, or whatever. If I said somebody's walking at 3 meters per second, you can picture that person more or less walking at that speed, right? You have a notion for speed. If I said I have a mass of 70 kilograms, you have a notion, an internal notion as to how big, roughly, how big a kilogram is. But you have, in all likelihood, no notion, no internal notion at least, as to how big a Coulomb is. A Coulomb is a massive unit, a very, very big unit. In fact, a Coulomb is so big that it takes approximately, this isn't exact, but approximately this many electrons in order to make a full Coulomb of charge. 10 to the 19 electrons or 10 to the 19 protons in order to make a full Coulomb of charge. So a Coulomb is a big unit. It's so big that we often don't actually see it expressed in questions as coulombs. We often see it expressed as maybe microcoulombs. A microcoulomb is 10 to the minus 6 coulombs. That conversion factor is on your data sheet, by the way. If you forget it, it's not a big deal. You also sometimes see it, occasionally see it, as a nanocoulomb, NC. A nanocoulomb is 10 to the minus 9 coulombs. These are fairly common because these are often what our charge is in terms of order of magnitude. Right? Using coulombs, using the unit for Coulomb is often like measuring distance in light years, right? We're not going to measure the distance from here to Calgary as 0.0000 whatever light years, right? We're going to measure it in meters or in kilometers because it makes more sense. So it often makes more sense to measure charge in nanocoulombs or in microcoulombs. Sometimes millicoulombs, and occasionally even coulombs. But don't be surprised when you see these units as well. Yep.
Is a Coulomb like something that like we use today, like that? But like when I'm charging my phone, am I using a Coulomb of energy, or is it?
Well, your phone charger is a 5-watt. Is most likely all these ones actually. It's not true. The little ones are 5-watt chargers. and the bigger ones are 10-watt chargers. And a watt is a measurement of power, not exactly coulombs, but a measurement of power, which is voltage times current. Okay, so voltage times current. And current, you're going to learn later on, current is a measure of the number of coulombs per second. Okay, so the voltage in these little charges over here, that are 5 volts. Okay, the voltage in the bigger ones are 5 volts as well, but the current ends up being twice as much in the bigger ones as it is in the smaller ones. And if the current is twice as much, then that means you have twice as many coulombs per second flowing into your phone.
Is that going to be like 1 coulomb per second, or will it be like a fraction?
Well, 1 coulomb per second is 1 amp. So a coulomb per second is an amp.
Okay.
So it's a lot of charge flowing per second that gives you an amp. Does that make sense?
I don't know what an amp is, but I think, yeah.
Well, I could answer that, but right now it wouldn't make a whole lot of sense to you, because my response would be, well, it's a coulomb per second.
Yeah.
Right? See, that's the whole point, though, right? Is that's out of your frame of reference, right? You're not familiar with those terms right now, so you can't picture when I say this many coulombs or this many amps. You can't picture that, whereas you can, because of experience, when I say 70 kilometers per hour, you can picture how fast that is. Okay? That's why I give you this number, so you have some kind of notion as to how big that is now. Okay? All right, so what is the charge of an electron? It takes a whole lot of them in order to give us a coulomb of charge. If you look at your data sheet, you actually can find the charge of an electron in the data sheet in the top right-hand corner. Over here we see an electron has a charge of minus 1e, and a proton has a charge of plus 1e. An alpha particle, whatever that is, plus 2e. Okay, we'll worry about that later on down the road. Positron is plus 1e. For now, we're just focusing on the electron and the proton, minus 1e and plus 1e. But what's an e? Minus 1e plus 1e. We just measured charge in coulombs, right? Why are we using an e now? An e is what we call the elementary charge. It is, I was going to say the smallest possible charge you can have. We'll go with that for now. The smallest possible charge that you can have. So an electron is negative 1 times that, and a proton is positive 1 times that. Now, how do you know what the smallest possible charge you can have is? Well, luckily it also says that on your data sheet. If you look over here on the left-hand side of your data sheet, you can see that an elementary charge is 1.60 times 10 to the minus 19 coulombs. So we're going to say that an electron is negative 1 times 1.6 times 10 to the minus 19 coulombs, which gives me an overall charge of an electron of negative 1.6 times 10 to the minus 19 coulombs. Right? Like, that's a small charge. That's why it takes so many of them to make a coulomb of charge. Charge of a proton, plus 1 times the elementary charge, or plus 1 times 1.6 times 10 to the minus 19, or we'll just say plus 1.6 times 10 to the minus 19 coulombs. Exactly the same charge, opposite nature of charge. One's positive, one's negative. Yep. Here's a few examples of what I call ion notation. I don't really know what you call it, but I just call it ion notation because it represents charges of ions. You don't need to remember that aluminum, or as we call it now, I guess, aluminium, is plus 3. Doesn't make any difference, right? If you need this, you'll be given this. I just want you to be able to read it and understand. It's kind of like music, right? If you're in band, you're not expected to remember the music to a certain song. Okay, you'll be given the music. You just need to be able to read the music. Okay, I don't expect you to remember that aluminum or aluminium is plus 3. I just expect you, if I give you Al plus 3, I expect you to be able to read that and tell me that the charge is plus 3. But plus 3 what? Coulombs? Yeah. Plus 3 elementary charges. So yeah, so we're going to say that this is plus 3 times 1.60 times 10 to the minus 19. In other words, this ion would have a charge of plus 4.8 times 10 to the minus 19 coulombs. So don't memorize that. Like, I don't even care if you have these examples written down, as long as on a test, when you see Al3 plus or Na plus or H plus or some other completely different thing, you're able to determine what the charge is based on the notation that you're given there. Na plus doesn't say 1, 2, 3, 4. What is it? If it doesn't say, it's going to be 1, right? So we're going to say the charge here is just plus 1.60 times 10 to the minus 19 coulombs. And this is sodium ion, where we have one more proton than electron. The number of protons in sodium is, I don't remember what it is actually. Might be, is it 11? 11 for the atomic number? Okay, I'll believe you. It rings a bell actually. So a sodium atom has 11 protons and 11 electrons, right? A sodium ion here has 11 protons and 10 electrons, right? That's all we're saying with this, is that we have one less electron than proton in this particular ion. Oxygen 2 minus, well, that just means that we have a charge of negative 2 times 1.6, or we'd say negative 3.2 times 10 to the minus 19 coulombs. In this case, we have 2 extra electrons, right? Oxygen, I think, is 8, atomic number 8. No, I think you're thinking of the mass number. Yeah. The atomic number is 8, which represents the number of protons, and therefore this would have 10 electrons. So just be able to recognize the notation, not these specific examples, just the notation that we use to describe that. Okay, I got a little example for you here. So our example says a balloon is rubbed against your hair, and it gains a charge of negative 9.6 times 10 to the minus 9 coulombs. Quite a bit of charge, right? This would be 9.6 nanocoulombs of charge. 9.6 nanocoulombs of charge. Determine how many electrons the balloon has gained or lost. Let's answer the second part of the question first. Is it gained or lost? Have the electrons been gained or lost here? How do you know it's been gained? Good. Yep. Negative 9.6, it's negative charge. We must have gained electrons. You don't become negative by losing negative. You become negative by gaining negative. So we're going to say that the electrons have been gained. Now the question is, how many have been gained? Let me give you a little analogy to help lead to this, okay? If I went to Sobeys and I said, and I picked up an orange, and I weighed it, and that orange weighed 100 grams. And then I picked up a bag of oranges, just a random size bag of oranges, and I took it to the cashier, and the cashier weighed it, and it weighed 700 grams. How many oranges would I have? Let's assume they all weigh the same. How many oranges would I have? 7, right? How'd you figure that out? 100 times 7? Or maybe 700 divided by 100? Gives you 7. We divided, right? 700 divided by 7 gives me, 700 divided by 100 gives me 7. So we took the total mass and we divided it by the mass of one orange. That's intuitive, right? When we're dealing with numbers that are relatively simple, like 700 and 100, like that's fairly intuitive. When we're finding the number of electrons, we're going to do something similar, except that we don't know the total mass of the electrons here, or even right now the mass of one electron. But we do know the total charge, and we know the charge of one electron. So instead of, when finding the number of electrons, dividing the total mass by the mass of one, we're going to divide the total charge by the charge of one. Q, by the way, stands for total, or sorry, charge for charge. Charge total divided by the charge of one. Now the total charge is negative 9.60 times 10 to the minus 9 coulombs, and the charge of one electron is negative 1.60 times 10 to the minus 19. This one on the top should be 10 to the minus 9. So let's do the math here. We're going to say negative 9.6 times 10 to the minus 9 divided by negative 1.6 times 10 to the minus 19. You're going to get a big number or a small number? Pretty big number, yeah. Right. In fact, 6 times 10 to the 10. 6 times 10 to the 10 electrons. Like, we're still nowhere close to a Coulomb of charge, because it takes about 10 to the 19 electrons to make a Coulomb of charge, but it's a lot of electrons still. Yep.
I don't understand how you got Q1.
How do I get Q1? Q1 is the charge of one electron. If you go back here, right, the charge of one electron is negative 1.6, right? And we're finding the number of electrons gained or lost. Well, the ones we had balance out with the number of protons, so they're really irrelevant here. The ones that we've gained all have a charge of negative 1.6, so we're going to simply divide the total excess charge we have by the charge of 1, just like we divide the total mass of the oranges by the mass of one orange. Yep. Good question. What would the units be here? You could say electrons, or you could just say it's a number, right? If I said, how many fingers do you have on your left hand? What's the answer? You could say 5, or you could say 5 fingers, right? How many electrons do we have? 6 times 10 to the 10. Or we could say 6 times 10 to the 10 electrons. Good question. Yep. Daniel?
Since the sign matters for charge, how do we have it as a vector? Is that another term?
No, that's a good question. Great question just asked. Negative until today, has always meant for us a direction. So if we had a negative velocity, it would mean left, or it would mean south, or it would mean west, or something like that, right? Whatever we define it as. Negative here doesn't mean direction. Okay, charge is a scalar. We can have a negative charge without it being a vector, because that negative doesn't indicate direction. It relates to the fundamental nature of this charge, the nature of this charge. It's either positive by nature or it's negative by nature, okay? As opposed to indicating something with direction. Now, later on in the unit, when we're going to do problems involving electric force, if you're not careful, you can mix up those two sign conventions, right? Because when you're talking about force, negative means left. When you're talking about charge, it doesn't mean left or right at all, right? So we got to be careful, but I'll point out how to deal with that when we get to it. You see at the back of the room here, got a few things written out here, including on the left-hand side, our always list. Always, under our always list, you can see when force and time appear in the same question, we do impulse, right? When we get a force versus time graph, we think area equals impulse. When we have a collision or explosion, we think conservation of momentum. The fourth thing I have listed here just says number equals AT divided by A1. What I mean by that is this. When you want to find a number of something in physics 30, and you're going to have to do this more than once, not just with electrons, but with other things, photons, whatever. You're going to take the total amount of something and divide it by the amount for 1. It might be the total mass by the mass for 1. It might be, as in this case, the total charge by the charge for 1. It might be the total energy by the energy for 1. Whatever it is that you have. It shouldn't be too confusing, because you do it with whatever you have. If you've got mass for 1 and total mass, divide the masses. Charge, divide the charges. If you get the energies, divide the energies. Got it? But you're always going to want to do total divided by the amount for 1. Good? Let's define a couple quick terms before our break here. In the context of electricity, not in the context of heat. You guys did a heat unit, I think in Science 9, I want to say, long enough ago that you probably don't remember it. You would have defined a conductor and an insulator in that context as well. This is completely different. Okay, a conductor in the context of electricity is what? You guys might have a notion of this already. Yeah? Okay. Okay, something that lets the electrons pass through pretty easily. Sure. Give an example of a good conductor. Yeah.
Copper wire.
Copper wire is a great conductor. It's not necessarily the best, but it's a great conductor still. Yep. Gold is a fantastic conductor, better than copper. That's why we have. That's why, by the way, we have. That's why we have sometimes when you have electronics cables or gold-plated cables. Right? Salt water, yes. In fact, water with all kinds of different things in it, right? Impurities in it like that. Yep. Yeah, pretty much all metal. What most of these things have in common are metals, the exception of salt water, right? Most of the good conductors are metals, and the reason that most of the conductors are metals is because if you take chemistry, you might know that metals have electrons on their outermost levels that aren't as tightly bound. So it's easier for those electrons to leave. That's why metals can become good conductors. We're going to define a conductor as a material in which electrons in the outermost regions of the atom are, I don't know if I said that right, free to move. Maybe we should have said freer to move than in nonmetals, but you get the idea there. And for sure, the best example of this typically is metals, although not always. There's something called a superconductor, which conducts even way better than things like metals, but it only happens at really low temperatures. And those aren't metals at all. Those tend to be more like ceramic type stuff. But it doesn't work at room temperature. It only works at, minus 200 or something. Now our other term is an insulator. And you can imagine an insulator is the opposite of a conductor. An insulator is a material in which the electrons are fairly tightly bound to the nucleus and are not, well, I should say not free, not as free to move around within the substance. Insulators can conduct. Tell me an example of an insulator. Rubber is an example of an insulator, yes. Now, rubber will conduct electricity. It just doesn't conduct electricity nearly as well as metals do. Plastic is another good example. It conducts, just not nearly as well. If you're standing out in a lightning storm and you're wearing rubber-soled shoes, you're not good. You're not protected because the rubber on the soles of your shoes will not protect you from the lightning, and the lightning will go right through them easily. Yet rubber's an insulator. It just doesn't conduct nearly as well as, let's say, if you had steel shoes on or steel toe boots or something like that. Although, quite frankly, in the case of lightning, it's not going to make much of a difference. So it's a material in which the electrons are not as tightly bound to the nucleus. They're not as free to move. Some examples of this would be plastic, rubber, and so on. Non-metals, right? Have a look at the table up here, the chart up here. You don't need to remember this or write this down or even remember it, but I just want to illustrate to you that clearly, if we look at the relative magnitude of conductivity, this isn't a measure like in any kind of units of conductivity. It's just compared to other things, right? Silver is clearly very high, 10 to the 8, right? Compared to, say, aluminum and iron, somewhere around 10 to the 7. So silver is about 10 times better than iron is of a conductor, even though they're both good conductors. But when you look at rubber, 10 to the minus 13 or so? Okay, that would mean that aluminum would be like 10 to the 20 times better of a conductor than rubber. Doesn't mean that rubber doesn't conduct. It just means that aluminum would conduct a lot better, right? You see on the top there, these things that are good conductors generally are metals, and these things that are really, really poor conductors or really good insulators are things like wood and glass and rubber and plastic and so on. One more page here before we finish it off for the day. We have 3 laws of electric charge that you may or may not have heard before. You probably have at some point. You just might not remember them necessarily. The 3 laws of electric charge are these, in any particular order. It's not like Newton's laws where they have to be in a particular order. Okay, one of them says opposite charges attract each other, which means if you have something that's positive, something that's negative, they're going to attract each other. Right? A positive, the hair on your head that's positive as a result of rubbing against the balloon will attract the negatively charged balloon. Okay, if you have a proton, it will attract an electron. Opposite charges attract each other. that come together. Like charges repel each other. Just like sometimes when you have two people that are too much alike, they repel each other. They don't do well together. They push each other apart. When you have positive, that will push away a positive. If you have negative, that will push away a negative charge. The third one, again, in no particular order, the third one that we have listed here says charged objects attract neutral objects. Now, this is a really important word. I'm not going to explain entirely why it's so important today. That's going to come tomorrow. But it is important. Okay, if you have a if you have a positively charged object, it will attract a neutral object. The balloon that's become negative by rubbing it against your hair will attract a negative wall, and that's why it'll stick to the wall for a little while. A positive object will also attract a neutral object. But, listen carefully, a proton will not attract a neutron, nor will an electron attract a neutron. Not electrically. A proton will attract a neutron by, remember that force, what that force is called? The strong nuclear force, but it won't attract it electrically. Okay? Positive does not attract neutral. Charge does not attract neutral. You have to have a neutral object, not just a neutron, but a neutral object that is made up of protons, neutrons, and electrons. And tomorrow you'll see why that's the case.